before the first dawn, there was no horizon. No galaxies, no suns, no constellations to trace across a night sky. Only an ocean of darkness, stretching in every direction, cold and unbroken. In that primal void, the newborn universe was still an infant, less than 200 million years old. Space was vast but empty of light, filled only with the faintest breath of hydrogen atoms, drifting silently as the cosmic expansion pulled them farther apart. Time itself seemed to move without witness, for there were no eyes, no planets, no life, only darkness. This was the cosmic dark ages, an epoch when physics tells us the universe should have been blind. The first stars, massive, short-lived giants, had not yet flared into existence. No galaxies had yet spun themselves into form. The only glow was the fading afterheat of the Big Bang, stretched so far by expansion that it whispered only in the cold radio tones of the cosmic microwave background. Yet, through the vast silence of this starless night, the James Webb Space Telescope has seen something it should not have seen. A faint, ancient light, older than the first suns, older even than the first galaxies. Photons born before any stellar fire existed, arriving now at the edge of human perception. It is light that by our current models should not exist. And yet, it is here. Real, measurable, undeniable. Is it the ghost of some primordial engine, burning before the stars? A whisper from physics beyond what we understand? Or is it a message carried across 13 billion years from a chapter of the universe we were never meant to witness? A light from a cosmos that should have been dark. In the cold geometry of space, far beyond the pole of Earth's weathered atmosphere, the James Webb Space Telescope drifted in its halo orbit around the second Lagrange point. Here, 1.5 million kilometers from the blue planet, it was neither fully still nor fully in motion. Balanced between the gravitational tug of Earth and the Sun, cradled in a pocket of stability that allowed it to keep its golden mirror turned forever outward into the abyss. This was no ordinary observatory. Webb's 21-foot hexagonal mirror, a mosaic of 18 gold-coated beryllium segments, was the largest ever sent into space. Each piece was polished to atomic smoothness, then assembled into a surface so sensitive it could detect the heat signature of a single bumblebee from the moon. But Webb's genius was not in its size alone. It was in the spectrum it sought. Where human eyes and older telescopes hunted visible light, Webb searched for the long-stretched whispers of ancient photons. Light so old that the expansion of the universe had pulled it into the deep infrared. Infrared was the language of the past. Every galaxy, every star, every planet we see today speaks in this language if we wait long enough. The further back we look, the more the expansion of space drags their light into redder and colder tones. The earliest light in the universe, from the first stars and galaxies, is invisible to ordinary detectors. But Webb was born to catch it. Its near-infrared camera, NIRCam, could map the faint glow of the first luminous objects. Its near-infrared spectrograph, NIRSpec, could break that glow into its elemental fingerprints, revealing what atoms existed when the light was born. From the moment the telescope was conceived, there was one ambition that overshadowed all others: to look farther back in time than humanity had ever seen, and perhaps to glimpse the universe as it emerged from its first darkness. This meant piercing the cosmic dark ages, the epoch after the Big Bang's afterglow had faded, but before the first stars had ignited. Cosmologists predicted this period to last until about 200 million years after time began. Until then, the universe should have been black, save for the cooling microwave haze of the Big Bang itself. The most promising windows into that abyss were carefully chosen: the Jade's Deep Field and the Cosmic Evolution Early Release Science Survey, CEERES region. The Jade's Field, a collaboration between the JWST Advanced Deep Extragalactic Survey and teams from Cambridge, Arizona, and across the globe, was selected for its emptiness. No bright stars to contaminate exposures, no nearby dust clouds to scatter light. Just a thin, clean slice of sky through which ancient photons could pass undisturbed for more than 13 billion years. The CEERS, led from the University of Texas, targeted another region, a stretch of sky in the constellation Bootes. Here, gravitational lensing by massive foreground structures could act as a natural magnifying glass, boosting the signal from galaxies and sources too faint to detect otherwise. Together, these fields were not random coordinates. They were archaeological dig sites in space-time itself. The observing runs began in the quiet hum of deep space precision. Webb locked its gaze on the Jade's field for dozens of hours at a time, its gyroscopes holding it perfectly steady. Layer upon layer of exposures accumulated, each one capturing photons that had been on their journey since long before Earth existed. Raw data streamed down to the Space Telescope Science Institute in Baltimore, where supercooled detectors recorded every speck of light. At first, the images revealed what had been expected: galaxies at redshifts of 8, 9, even 10, their light coming from just a few 100 million years after the Big Bang. These alone were thrilling confirmations of Webb's power. But as the NIR SPEC instrument began to analyze the spectra, something emerged that made the teams pause. There, hidden in the faintest smudges of the deep field, were sources whose redshifts were not 8, not 10, but 15, and perhaps even higher. That placed them not at 400 million years after the Big Bang, but at less than 270 million. This was still the universe's dark age, when theory said no stars had yet been born. The first to notice the anomaly was Dr. Brant Robertson, a cosmologist at the University of California, Santa Cruz, working on Jades. Robertson had spent his career predicting what Webb might find and what it could not. In his models, galaxies at redshift 15 were possible only if the first stars formed much earlier than the prevailing lambda CDM cosmology allowed. He stared at the early spectra, searching for error. In the UK, Dr. Emma Curtis-Lake of the University of Hertfordshire was poring over the same data. A specialist in high redshift galaxy conformation, she had long dealt with the false promises of faint, noisy detections. These could be noise spikes, she thought, running the numbers again. But the features in the spectra, subtle dips and rises in the light curve, matched no instrumental artifact she knew. They were consistent, repeatable, and most tellingly, they appeared in multiple filters. Meanwhile, halfway across the world, Dr. Stephen Finkelstein at the University of Texas was leading the CEERS analysis. His team had uncovered sources with similar extreme redshifts. At first, he assumed they were simply dusty galaxies at lower redshifts, a common trap in deep surveys, where intervening material can redden light. But spectroscopy told a different story. The absorption breaks and emission lines did not align with that interpretation. For weeks, the teams exchanged encrypted data files and long, meticulous emails. The process was slow by design. Every possible false positive had to be eliminated. Cosmic ray hits on the detectors? Ruled out. Improper flat fielding of the images? Checked and cleared. Misidentified spectral features? Cross-matched with simulations and known galaxy templates. Gravitational lensing contamination? Carefully modeled, and found insufficient to explain the brightness. As the possibilities narrowed, the weight of the data grew heavier. These photons were old beyond reckoning, older than the first stars by the standard timeline. The mystery was no longer whether the detections were real. It was whether cosmology itself would need to shift to accommodate them. Inside the analysis rooms, there was an unspoken electricity. At the Space Telescope Science Institute, a small group gathered for what they called redshift nights, evenings when the latest spectra were plotted on giant screens, and everyone present tried to poke holes in the findings. Graduate students, senior astronomers, and mission veterans all leaned in, sometimes arguing over tiny inflections in the spectral lines. Yet each test the signals survived made them more undeniable. The shock was profound because it struck at the heart of the universe's timeline. If luminous objects, whatever they were, existed at redshift 15 or beyond, then the processes that ended the cosmic dark ages had begun earlier and under stranger conditions than any model had anticipated. Perhaps the first stars formed not 200 million years after the Big Bang, but 100 million. Or perhaps some entirely different phenomenon lit up the young cosmos. Accretion onto primordial black holes, decay of exotic particles, or bursts from collapsing dark matter halos. The possibility that this was not starlight at all, but something more exotic, thrilled and unsettled the researchers in equal measure. Starlight, we understood. Starlight had a place in the great unfolding story of cosmic evolution. But this was like finding a lamp lit in a house before the house had been built. Robertson recalled an earlier moment in astronomical history, 1998, when observations of distant supernova revealed the accelerating expansion of the universe. At the time, the idea of dark energy had been barely more than a theoretical curiosity. Now it was a cornerstone of cosmology. This, he thought, could be another one of those moments. Curtis Lake, in contrast, felt the creeping caution of a scientist aware of how easily the extraordinary can crumble under scrutiny. She kept reminding her team to resist the narrative temptation, to let the data speak only as far as it could. Yet even she admitted, privately, that the light they were seeing had a signature unlike anything in her career. By early autumn, the convergence was undeniable. Independent pipelines, different instruments, separate survey fields, all pointed toward the same conclusion. Photons from before the cosmic dawn had found their way into Webb's detectors. The wider scientific community began to take notice. Preprints appeared on archive, some cautious, others bold. A few proposed radical revisions to the timeline of structure formation. Others called for patience until more data arrived. But in the quiet offices where the anomaly had first been spotted, the sense of standing at the edge of a profound shift only deepened. Webb had been designed to find the universe's first galaxies. Instead, it had found something even more elemental, a hint that light itself may have emerged under circumstances we do not yet understand. And for the scientists who first traced those faint, stretched photons back to their impossible birthplace, the realization was as humbling as it was exhilarating. The story of the universe's beginning was not just incomplete, it had been missing an entire chapter. The first wave of data had barely settled into the archives when the doubts began. In the high-ceilinged meeting rooms of the Space Telescope Science Institute, in late-night conference calls stretching across time zones, the tone was a mixture of exhilaration and restraint. The James Webb Space Telescope had delivered something extraordinary. Redshift measurements pointing to a universe alight before the first stars. Yet in science, the extraordinary is also the most fragile. The anomaly was not a simple curiosity. It was a direct challenge to the established chronology of cosmic history, a timeline refined over decades from the combined weight of theory, observation, and simulation. According to the lava constant theta model, the concordance cosmology, the sequence was clear. After the Big Bang, there was the blinding light of the first few 100,000 years, then the cooling silence of the cosmic dark ages, followed by the ignition of the first stars around 200 million years later. Webb's faint spectral lines, placed at redshifts of 15 and beyond, intruded into that silent epoch like whispers in an empty cathedral. To many, that was reason enough to suspect a flaw. Extraordinary claims demand extraordinary evidence, the mantra went. And in the cautious discipline of cosmology, extraordinary claims also demand extraordinary skepticism. The first wall of doubt for Dr. Emma Curtis Lake, whose career had been built on separating genuine high redshift galaxies from imposters, skepticism came naturally. In early team calls, her voice carried the tempered caution of experience. "We've seen this before. Not at this magnitude, but we've seen candidates that fall apart under scrutiny." She was referring to the long history of false dawns in astronomy. Faint smudges later revealed as nearer galaxies obscured by dust, or instrument glitches masquerading as distant light. The calibration of NIR SPECS detectors was meticulously designed to prevent such errors, but the faintness of these signals meant the margin for mistake was thin. Cosmic rays could leave ghost traces in the imaging. Subtle temperature fluctuations could introduce artifacts. Even the sequence of filter exposures could produce misleading colors. The JWST team began a line-by-line audit of the data pipeline. Flat field calibrations were reapplied. Background noise maps were reevaluated to ensure no faint glow from the telescope's own structure was contaminating the field. Parallel datasets from the CEER survey were pulled for comparison. The process was painstaking. Each test was designed not to prove the signal right, but to break it. The weight of consensus across the Atlantic. In the University of Texas offices, where the CEER data was being processed, Dr. Stephen Finkelstein faced his own internal divide. He had seen enough to believe the anomaly was real, yet he knew the cost of moving too quickly. In astronomy, premature conclusions can echo for years, staining entire datasets with doubt. "We have to assume," he told his team, "that there's a flaw we haven't found yet. If it survives that, then we'll talk about rewriting textbooks." The idea that the universe might have harbored luminous phenomena before the first stars was intoxicating. But intoxication was dangerous. The community remembered 2014, when the BICEP 2 experiment claimed detection of primordial gravitational waves from inflation, a discovery later attributed to galactic dust. That cautionary tale hung over every conversation now. Cosmology under siege. If the redshifts were correct, the implications were staggering. In the Standard Model, the birth of the first stars, population 3, marked the end of the Dark Ages. These stars formed from pristine hydrogen and helium, their short lives flooding space with ultraviolet light that reionized the universe. But Webb's signals were coming from a time when, by this model, gravitational collapse had not yet had time to create such stars. If these were not stars, then what were they? Some theorists speculated about primordial black holes, relics from the earliest instance after the Big Bang, whose accretion disks could blaze brightly in the infrared. Others suggested dark matter decay, where exotic particles might have transformed directly into photons. More speculative still were ideas involving cosmic strings, hypothetical defects in space-time left over from phase transitions in the infant universe. Releasing bursts of energy. Each of these possibilities strained the limits of known physics. Each carried implications far beyond astronomy, touching particle physics, quantum field theory, and even the geometry of space-time itself. For the Lambda CDM model, the most successful cosmological framework in history, confirmation of such phenomena would be nothing less than a paradigm fracture. In September, a closed-door session at the European Southern Observatory brought together key figures from JWST, CEERS, and several independent teams. The mood was disciplined, almost surgical. Screens displayed the spectra, tiny, jagged lines against dark backdrops, each labeled with redshift estimates, confidence intervals, and signal-to-noise ratios. These features, said a spectroscopist from the University of Geneva, pointing to a sharp drop in flux, are exactly where Lyman breaks should be. If these were galaxies, a voice from the back countered, or where certain instrumental artifacts can appear under specific thermal conditions. The discussion was not heated, but it was relentless. Every piece of data was challenged. The teams replayed the original observations in simulation software, feeding in mock signals to test how the pipeline would process them. In each trial, the anomaly persisted. There was precedent for this kind of tension. In 1929, when Edwin Hubble published his measurements of the expanding universe, many refused to believe the cosmos could be dynamic. In the 1960s, when Arno Penzias and Robert Wilson stumbled upon the cosmic microwave background, they thought it was pigeon droppings in their radio horn. Revolutionary data often wore the mask of error until the weight of replication made it impossible to ignore. For Webb's findings, replication would be harder. Observing at such extreme redshifts required not only deep exposures, but perfect conditions, with no contamination from foreground light. And yet, the rarity of the sources meant they could not simply be re-imaged on demand. The sky did not always cooperate. To the public, Webb's early results were celebrated as a triumph. Stunning images of galaxies, nebulae, and gravitationally lensed arcs filled headlines. But the anomaly remained unannounced, locked in the guarded discussions of the collaboration. The fear was that releasing it prematurely would unleash a storm of speculation before the science was ready to withstand it. Behind the scenes, however, the debates sharpened. At Caltech, a team analyzing gravitational lensing patterns noted that some of the high redshift candidates appeared brighter than expected for their supposed distance, suggesting either that our understanding of early luminosity was wrong, or that some magnifying effect was at play. At Princeton, theoretical cosmologists began rerunning structure formation simulations with altered parameters, trying to see if star formation could be pushed earlier without breaking other constraints, such as the cosmic microwave background's observed uniformity. Most runs failed. Pushing star formation earlier often meant violating other well-tested measurements, like the abundance of light elements predicted by Big Bang nucleosynthesis. The scientists found themselves split between two mindsets. One was the builder's caution, the instinct to defend the structure of cosmology that had been assembled over decades, resisting the pull of a single outlier observation. The other was the explorer's hunger, the recognition that every great leap in science begins with an outlier observation. In long email threads, Robertson wrote of his excitement tempered by realism. If this holds, we will have to revisit some very basic assumptions, but we have to let it survive every possible way it can be wrong first. Curtis Lake replied with her own metaphor. It's like finding footprints in snow we thought was untouched for centuries. They may be real, but before we say they are, we have to make sure no one else has walked this way unseen. Verification took many forms. Teams compared Webb's detections with older Hubble Deep Field data, searching for any trace of the same sources in optical light. In most cases, there was none, consistent with extreme redshift, but also consistent with noise. They cross-matched the coordinates against known catalogs of brown dwarfs and other local infrared sources, ensuring they were not mistaking nearby faint objects for cosmological relics. Spectral fitting was refined using Bayesian analysis, allowing the redshift probability distributions to be calculated with high precision. In several cases, the peak probability still lay squarely in the pre-stellar epoch. Gradually, the tone began to change. By late autumn, after months of attacks on the data, the anomaly had survived. It was no longer dismissed as a probable error. It was now treated as a provisional fact, a fact that demanded explanation. And with that shift came a new kind of shock. The implications were not just that our timeline was wrong, but that our picture of the early universe might be missing entire categories of physics. If the light was not from stars, then some other luminous process had taken place in the first few 100 million years, one powerful enough to be seen across the expanding void. The cosmic dark ages, long thought to be absolute, might have been punctuated by brief, brilliant events we have only now begun to glimpse. The scientists knew the world would eventually learn of this, but they also knew that the questions it raised would be harder to answer than the detection itself. To claim discovery was one thing. To explain it without tearing at the fabric of the rest of cosmology was another. The next steps were clear. More deep field exposures, wider surveys, and cross-checks with upcoming missions like the Nancy Grace Roman Space Telescope. Independent teams would need to re-observe the same fields, perhaps catching the faint glow of similar sources elsewhere. For now, the reaction remained a mixture of awe and unease. Awe at the possibility that the universe's first light was not starlight at all. Unease at the knowledge that, if true, it would force humanity to redraw its oldest map, the one that begins at the beginning. In the control rooms, where James Webb's deep field data was first assembled into images, the work shifted from discovery to dissection. What had once been a pattern of faint smudges on the edge of visibility was now a puzzle to be unraveled photon by photon. The telescope's detectors had captured light so stretched by the universe's expansion that it lay deep in the infrared, the invisible spectrum where ancient signals hide. To understand what these signals were, the raw numbers had to be stripped of everything they had gathered in their journey. The noise of the detectors themselves, the faint thermal glow of the telescope, the haze of cosmic rays, and the slow heartbeat of the electronics that read each exposure. At the heart of this process was spectroscopy, the act of breaking light apart into its constituent wavelengths, turning a simple image into a code that could reveal its origins. Webb's NIR-SPEC instrument had done this with a precision unmatched by any telescope before it. Each photon from these mysterious sources carried a unique imprint, a subtle modulation in brightness across wavelengths that acted like a fingerprint of the matter that produced it. Astronomers examined the positions of the absorption breaks, the dips where photons had been absorbed by intervening hydrogen, and the emission lines, the spikes where certain elements had released light at characteristic energies. The most striking feature was the Lyman alpha break, the point where light from the far ultraviolet was absorbed by neutral hydrogen in the early universe. In these signals, that break had been shifted so far into the infrared that its position corresponded to redshifts well above 15. It was a silent confirmation that these photons had been traveling for more than 13 billion years, emitted when the universe was still a fraction of a billion years old. Yet the spectra did not entirely match what would be expected from ordinary galaxies filled with population 3 stars. Instead of the complex forest of absorption lines left by generations of stellar birth and death, the patterns were sparse, almost too clean. It was as though the sources lacked the heavier elements, carbon, oxygen, iron, that later stars would forge. This absence was not unexpected. The first luminous objects would have been formed from pristine hydrogen and helium alone. But here, there was something stranger. In some cases, the continuum of light was smooth and unbroken, more like the thermal emission from heated gas falling into a black hole than the combined output of many stars. Astronomers began to run models to match these spectral shapes. They simulated accretion disks around black holes formed not from collapsed stars, but perhaps directly from the collapse of massive clouds of primordial gas. Such direct collapse black holes could in theory ignite early, feeding on surrounding matter and glowing in the ultraviolet, their light stretched into the infrared by cosmic expansion. Others tried to fit the spectra to scenarios where exotic particles decayed into photons during the Dark Ages, producing a diffuse background glow. The data from NIRCam added another dimension. Webb's imaging could measure not only the brightness of these sources, but also their apparent size and morphology. Many of them appeared point-like, unresolved even at Webb's extraordinary resolution. That was consistent with either very compact galaxies or single, extremely bright objects. In a few cases, faint, extended halos suggested that some of these sources were embedded in larger structures, perhaps the earliest proto-galaxies still in the act of formation. To test whether gravitational lensing might have magnified the signals, researchers mapped the positions of known massive galaxy clusters in the foreground. In some instances, lensing seemed plausible and could account for the surprising brightness of a few candidates, but others lay in apparently empty regions of sky with no obvious lens to amplify them. If these were truly as luminous as they appeared, then the early universe was more efficient at producing bright sources than any current theory allowed. The analysis did not stop at morphology and spectroscopy. Teams examined the photometric redshifts, estimates based on broad color measurements across multiple filters, and compared them to the spectroscopic results. Usually, photometric redshifts are less precise, but in these cases, they agreed with the spectroscopic measurements to a remarkable degree. This reduced the likelihood that the sources were misidentified low redshift interlopers. Still, every possibility had to be considered. Could these be brown dwarfs or other cool stars within our own galaxy, masquerading as distant objects? Unlikely, given their lack of proper motion over months of observation and their mismatch with stellar spectra. Could they be artifacts caused by detector persistence, the lingering afterimage of a bright source observed earlier? Careful scheduling of exposures had minimized that risk, and the signals appeared in independent observations separated by days or weeks. With each eliminated alternative, the reality of the anomaly became harder to dismiss, but the deeper the data was dissected, the more the central mystery sharpened. If these were galaxies, they were forming stars far earlier and more rapidly than models predicted. If they were not galaxies, then some unknown mechanism was producing light in an epoch we thought was dark. In research offices around the world, computer simulations began to strain under new parameters. Cosmologists pushed the starting conditions of their models closer to the Big Bang, testing whether primordial density fluctuations could collapse quickly enough to produce luminous structures at such high redshifts. Most simulations failed, producing only small, diffuse clumps that would not have shone so brightly. To make the models match the observations, something had to change: the nature of dark matter, the efficiency of cooling in primordial gas, or the presence of some new physics entirely. Even the possibility of systematic error, though shrinking, could not be dismissed outright. Independent teams requested access to the raw, unprocessed data to rerun reductions with different pipelines. In every serious reanalysis, the high redshifts persisted, and with each confirmation, the urgency to understand grew. The faint light curves, stretched across the universe's age, became more than data points. They were like messages written in a language older than stars, waiting for a translation that science had not yet learned. Some astronomers spoke of them in almost poetic terms, as echoes from a chapter of cosmic history no one had expected to read. Others clung to caution, warning that nature has a way of disguising the ordinary in the costume of the extraordinary. And yet, the weight of the evidence pulled the community toward the same unsettling realization. Whatever these sources were, they did not fit neatly into the familiar sequence of cosmic evolution. They were not simply earlier examples of known phenomena. They were, perhaps, signposts pointing toward processes that had been invisible to us until now. In the weeks that followed, proposals were drafted for follow-up observations, deeper integrations on the same fields, aiming to improve the signal-to-noise ratio of the spectra. Parallel observations with different instrument configurations to confirm that the spectral features were not artifacts of Webb's optics. Plans for cross-survey comparisons with data from ALMA, the Atacama Large Millimeter Submillimeter Array, to search for traces of dust or gas that could reveal the nature of the sources. Every photon from these ancient lights was precious. They had crossed a universe still in its infancy, dodging absorption by neutral hydrogen, slipping through the slow rearrangement of matter into the cosmic web, avoiding the glare of later-born galaxies, until finally they fell upon the gold-plated mirrors of a telescope built by a species that had only just learned to look beyond its own sky. In the dim glow of their spectra, scientists could see not only the possibility of new physics, but also the fragility of knowledge itself. The timeline of the universe had always been drawn in broad strokes, constrained by what could be observed. Webb was now sketching details in a place where we thought there was only blank canvas. Whether those details would match the rest of the picture or force the painting to be redone remained the question that kept them watching the data long after the observation runs had ended. The earliest days after the anomaly's confirmation had been marked by restraint. The teams had worked in a language of probabilities, speaking of likelihoods and error margins, keeping speculation close to the chest. But as weeks turned to months, the data began to take on a different character, not because it changed, but because of what it refused to do. It refused to go away. It refused to be explained by the comfortable boundaries of established theory. Every fresh observation, every reanalysis, only deepened its defiance. The redshifts were no longer numbers written in the margins of a spreadsheet. They had become like coordinates pointing into a part of the cosmic map that no one had drawn. At z equals 15 and beyond, these sources belong to a time when the first galaxies should have been no more than loose gatherings of cooling gas. By every prior model, there should not have been enough structure, enough mass, enough time for such luminous entities to exist. Yet here they were, fixed points of light from an age still swaddled in the opaque fog of neutral hydrogen. The more the teams looked, the more unsettling patterns emerged. Some of the sources appeared brighter than any reasonable model of early star formation could allow, even if they were the mythical population 3 giants, stars tens or hundreds of times more massive than the Sun, burning ferociously hot and dying in only a few million years. If these were galaxies, they would have to be forming stars with an efficiency that bordered on the impossible, converting raw gas into stellar furnaces at a rate that violated known cooling timescales. Others displayed spectral slopes more consistent with accretion disks around massive black holes. But how could such black holes have formed so quickly? Even if the seeds were unusually large, direct collapses of vast primordial gas clouds, they would need to feed at nearly the maximum theoretical rate, the Eddington limit, without pause from the moment they were born. And even then, the numbers strained against the limits of plausibility. The absence of certain chemical fingerprints added another layer to the puzzle. If these were stellar populations, even the earliest ones, their light should bear hints of the first nucleosynthesis beyond hydrogen and helium, the metals forged in the cores of the most massive stars and released in their supernova deaths. But for several candidates, the spectra were almost too pure, too free of contamination. This could mean they truly were among the very first lights to ever shine, or that they were not stellar at all. The possibility of exotic origins began to move from the fringes of discussion toward the center. Theories that had once been shared only in side conversations began to appear in internal memos and draft papers. Could the signals be from the decay of exotic particles, relics from the earliest fractions of a second after the Big Bang? Some versions of dark matter, sterile neutrinos, axions, might release photons as they transformed into lighter particles. In the right conditions, this decay could produce a faint but measurable glow, one that would peak in the ultraviolet in the rest frame and arrive to us in the infrared. Others considered more radical scenarios. In the chaotic first instance of the universe, phase transitions in fundamental fields could have created one-dimensional defects in spacetime, cosmic strings. If such strings oscillated or collided, they could release bursts of energy detectable across cosmological distances. The light from such an event, passing through the still neutral medium of the Dark Ages, might emerge with a smooth, featureless spectrum like some of the candidates exhibited. None of these explanations were without problems. Each required conditions that were speculative at best, and each carried implications that would ripple across all of physics. To confirm any of them would mean rewriting not just the timeline of the early universe, but its very physical script. Observations in other wavelengths began to be considered. If the sources were black holes, they might produce X-rays detectable by sensitive space-based observatories. If they were exotic particle decay, there might be subtle signatures in the gamma-ray background, or in the statistical patterns of the cosmic microwave background. Proposals were sent to cross-check Webb's fields with data from Chandra, XMN Newton, and even archival maps from the Planck satellite. But Webb's own data continued to lead the charge. In longer exposures, the faint halos around some sources became more distinct. They suggested an interaction with the surrounding intergalactic medium, perhaps the beginnings of ionized bubbles forming around early light sources, eating away at the fog of neutral hydrogen. If so, then reionization, the great turning point when the universe became transparent, might have started earlier and proceeded faster than anyone had thought. This, too, was a shock. It was one thing to find early lights. It was another to find them powerful enough to alter the ionization state of the cosmos ahead of schedule. If confirmed, it would mean that the conditions for life, at least the basic transparency of the universe to starlight, arrived far sooner than the standard model suggested. The ripple effects spread into other disciplines. Theorists recalculated the timeline for the formation of heavy elements, the seeds of planets and biology. If star formation began earlier, then so too could the chemical enrichment of the cosmos. That would place the first potentially habitable planets earlier in cosmic history, not billions of years later, as once assumed, but perhaps within the first billion years after the Big Bang. The thought was dizzying. Somewhere in a universe still young and turbulent, the ingredients for life could have been stirring. Yet, for every bold extrapolation, there was a counterweight of caution. In private, some senior scientists warned of the seduction of anomalies. Nature had a way of offering mirages, phenomena that looked like new physics, but which dissolved under deeper scrutiny. The history of astronomy was littered with them. A spectral line thought to be evidence of a new element turned out to be oxygen in a rare state. A wobble in a star's motion, heralded as proof of a planet, proved to be instrumental drift. And so the work intensified. More fields were added to the observation queue. Longer integrations were scheduled. The teams began to collaborate across surveys, pooling resources and expertise. For JWST and CEERS, the goal was not simply to confirm the existence of high redshift sources, but to build a sample large enough to map their distribution, to see whether they clustered in ways that could reveal their nature. The months ahead would bring more photons, more spectra, more chances to see behind the veil. But even now, before the next wave of data, the mystery had already shifted in character. What had begun as an anomaly had become a challenge, a gauntlet thrown at the feet of modern cosmology. If the universe could shine before its first stars, then the rules we thought we understood were only part of the truth. Something else had been at work in the darkness, something powerful enough to light a cosmos still unformed. And as the scientists stared at the traces of that ancient light on their screens, they felt both the exhilaration of discovery and the weight of its consequence. For they knew that to explain it, they might have to ask questions that reached beyond galaxies, beyond black holes, beyond the comforting boundaries of known physics, into the deep, uncharted territory where the universe still keeps its oldest secrets. Point. The light was real. That much had been accepted, reluctantly at first, then with the quiet, heavy certainty that comes when every attempt to erase an anomaly only makes it more defined. But reality was not the same as understanding. To see the light was one thing. To explain it, to fold it into the logic of a universe whose earliest moments had already been so carefully mapped, was another. In the silence after confirmation, the conversation turned to causes. Scientists gathered in rooms lit only by the pale glow of spectra on wide screens, their faces washed in the color of the early universe. In the beginning, they spoke of it as one speaks of an unnamed shape in the dark, cautiously, without letting their voices lift too far into the realm of speculation. But as the nights stretched on and the data resisted the usual explanations, a small set of possibilities began to crystallize, each one strange in its own way, each demanding that some part of physics be bent to fit the shape of the signal. The first possibility was the most intuitive, that these were the very first stars, the long-theorized population 3 giants. Forged from pure hydrogen and helium, these stars would have burned hotter and brighter than anything in the present universe, unburdened by the heavier elements that slow nuclear fusion. Models had long predicted their existence, but no telescope had yet seen them directly. Their light would be swamped by later generations of stars, diluted by distance and time. For Webb to see them at redshifts beyond 15 would mean they had formed far earlier than expected, collapsing out of dense knots of gas in a universe still cooling from the fire of its birth. It was possible, but possible did not mean easy. Theoretical timelines suggested that even the fastest collapsing clouds would struggle to reach ignition within a few 100 million years, and the sheer brightness of some sources seemed to outstrip even these hypothetical titans. The next contender was darker. Not stars at all, but black holes. Specifically, direct collapse black holes, vast wells of gravity, formed when entire clouds of primordial gas collapsed inward without first fragmenting into stars. Such monsters could start life with masses tens of thousands of times greater than the Sun, skipping the slow growth from stellar seeds. As they fed on surrounding matter, their accretion disks could blaze with ultraviolet light, later stretched into the infrared by the expansion of space. In this view, the strange smoothness of some spectra was not a problem, but a clue, the mark of gas heated to millions of degrees as it spiraled into the event horizon. Yet even here, there were limits. For these black holes to shine so brightly so soon, they would have to consume matter at or above the Eddington limit for their entire existence, a feat nature rarely sustains. And their sheer abundance in Webb's deep fields raised a troubling question. If they were common then, why are their descendants so rare now? From the realm of astrophysics, the discussion drifted into the colder, more speculative corridors of particle physics. Could the light be the death cry of exotic particles, relics from the universe's first seconds? Certain dark matter candidates, sterile neutrinos, axions, are theorized to decay into ordinary particles, sometimes releasing photons in the process. If such decays occurred en masse during the Dark Ages, they might produce a diffuse, ancient glow, invisible until Webb's eyes found it. This theory had an allure. It offered a bridge between cosmology and the unseen majority of the universe's mass. But it also carried risk, for dark matter had never been observed directly, and tying its nature to an unexplained signal risked building a chain of inference with no anchor in known reality. A more exotic possibility reached further still into the very fabric of space-time. Some theorists spoke of cosmic strings, hypothetical one-dimensional defects left over from symmetry-breaking phase transitions in the early universe. If they existed, these filaments of immense tension could oscillate, snap, or interact, releasing bursts of energy on scales vast enough to be seen across cosmic history. The light from such events would be brief but potent, its spectrum shaped not by atoms or dust, but by the raw conditions of space-time itself. Detecting such an event would be a revolution, not only confirming an idea born in the mathematics of grand unified theories, but offering a glimpse into energies far beyond the reach of any human-made experiment. Yet here too, the evidence was thin, and the burden of proof would be crushing. There were other ideas, whispered more than spoken, their edges frayed by the sheer audacity of their implications. Some imagined that the photons Webb had caught were born not in our universe at all, but in a neighboring domain of the multiverse, their path bent across the boundary by gravity or quantum tunneling. Others wondered if what we were seeing was a kind of mirage, light from later times, distorted and multiplied by unknown structures in space-time, arriving at us with a false redshift. These notions sat at the far edge of plausibility, dangerous to voice too loudly in a field that depends on trust in its own discipline. And yet, the fact that they were spoken at all was a measure of how unsettling the observations had become. For each theory, the scientists traced the same careful arc of reasoning. What would it take for this to be true? What would it mean if it were? And what would it break in our current understanding? If these were early stars, then the rate of structure formation must be revised, perhaps demanding tweaks to the physics of cooling gas or the distribution of dark matter halos. If they were black holes, their seeds must have been planted by mechanisms we do not yet understand. Perhaps in the chaotic instance after inflation. If they were particle decays, we would have our first direct window into the dark sector and a new puzzle about why it happened then and not before or since. Every theory had its own signature, a pattern of evidence it would leave behind. Early stars should show traces of ionized bubbles around them, regions where their ultraviolet light had stripped electrons from hydrogen atoms. Black holes might reveal themselves in X-ray or radio follow-up observations, their accretion-powered jets piercing the dark ages. Exotic particle decays could leave faint imprints in the cosmic microwave background or the high-energy gamma-ray sky. Cosmic strings, if real, might also produce gravitational waves, faint tremors in spacetime that new detectors like LISA could one day catch. Follow-up proposals multiplied. Observations with ALMA could search for the faintest traces of dust, revealing whether these sources had already begun to enrich their surroundings with heavier elements. X-ray observatories could hunt for the telltale flicker of black hole feeding. Future surveys with the Nancy Grace Roman Space Telescope could widen the search, mapping the true distribution of these ancient lights across the sky. Each mission became a potential interrogator, asking the same question in a different language of physics. And yet, there was a current of unease beneath the optimism. The scientists knew that reality might turn out to be crueler than their speculation, that a more mundane explanation might wait just beyond the reach of the data. A subtle bias in the selection of sources, a rare form of lensing that had gone unnoticed, a property of early galaxies we had simply failed to model correctly. The danger was not only in being wrong, but in letting the seduction of mystery pull too hard against the anchor of evidence. Still, the light was there and it had to be explained. Theories were not mere intellectual exercises now. They were wagers placed on the nature of the universe itself. In every long meeting, in every quiet moment before another set of data loaded on the screen, there was the same unspoken admission that whichever theory survived, it would leave us with a cosmos stranger, more intricate, and more unpredictable than the one we thought we inhabited. The work ahead was vast. It would take years to gather enough evidence to favor one explanation over another, and perhaps decades to prove any of them beyond doubt. But for now, the field was alive with the rare electricity that comes when the universe sends us something we cannot yet name. A light older than stars, older than galaxies, a light that slipped through the fabric of time itself to reach a golden mirror drifting far from home. And as that mirror turned its gaze ever deeper into the dark, the scientists knew they were not just looking backward. They were peering into the boundary between what we know and what we do not. A boundary now lit, faintly, by something that should never have been there at all. The instruments that had first caught the impossible light were still orbiting in silence. But on Earth, the noise was growing. Not in the public sphere yet. There, the anomaly remained hidden behind the curtain of technical briefings and controlled releases. But in the laboratories, observatories, and theory groups that had been drawn into its gravity. The time for disbelief was ending. The time for testing had begun. To pursue an answer, science would need to wield every tool it possessed. That meant not only Webb itself, but the entire arsenal of modern astronomy, physics, and computational modeling. The light was ancient, but the pursuit of its meaning would be immediate and modern. Every wavelength, every technique, every instrument that could be turned toward this mystery was being summoned. Webb would remain at the center of the effort. Its NIRCam and NIRSpec instruments were already scheduled for deeper integrations, longer exposures that would catch more photons from each candidate source, sharpening the spectra until noise was stripped away and only signal remained. For the faintest objects, even a handful of additional photons could confirm or destroy the case for their extreme redshift. Teams began mapping out observation windows months, even years in advance, threading the targets through Webb's carefully balanced mission plan. But no single telescope could answer the question alone. To know whether some of these sources were accreting black holes, X-ray eyes would be needed. The Chandra X-ray Observatory, still operating decades after its launch, became part of the plan. Its instruments could detect the high-energy radiation produced when matter spirals into a black hole, a signature that no star could mimic. If Chandra saw the same coordinates flare in X-rays, it would tilt the scales toward the black hole hypothesis. If not, the field of contenders would narrow. On the high plateaus of Chile, another set of instruments prepared to listen for a different kind of evidence. The Atacama Large Millimeter Submillimeter Array, ALMA, was tasked with searching for the cold signatures of dust and gas around these distant sources. If dust was present, it would mean that at least some generations of stars had already lived and died in these regions, enriching the medium with heavier elements. A detection of dust at such an early time would push the limits of star formation theories, hinting at a far more rapid chemical evolution than expected. If no dust appeared, the case for primordial light, untainted by stellar death, would grow stronger. Gravitational lensing was another tool in the arsenal. If massive clusters of galaxies lay between Earth and the early sources, their gravity could bend and magnify the light, making faint objects appear brighter and more distant than they were. To map the distribution of potential lenses, astronomers turned to the Hubble Space Telescope and ground-based observatories with adaptive optics systems. Pinning down whether lensing was amplifying the anomaly was critical. If it was, the true distances and ages of some candidates could shrink, collapsing the entire mystery for those objects. Spectroscopy, however, remained the most direct path. Here, collaboration extended to the next generation of ground-based giants. The extremely large telescope in Chile, with its 39-meter mirror, was still under construction. But its planned spectrographs would, in time, make possible the kind of detailed analysis Webb could not perform alone, resolving the chemical fingerprints of these sources with unprecedented precision. Even beyond the realm of light, other messengers were being considered. If the sources were massive black holes, their mergers might produce gravitational waves, ripples in spacetime, strong enough to be detected by future space-based observatories like LISA, the Laser Interferometer Space Antenna. This was a longer bet. LISA would not fly for years, and the signals would be rare. But in the minds of the scientists drawing the network of possible tests, no channel was too remote to consider. Meanwhile, in the data centers, computational simulations grew in scale and ambition. Supercomputers were fed with altered cosmological parameters, faster structure growth, heavier initial seeds for black holes, more efficient cooling of gas, to see which combinations could reproduce the number and brightness of the observed sources. Each run was a universe unto itself, a model from the Big Bang forward, its laws tuned to see whether reality could be bent just enough to match the strange lights in Webb's images. Most failed. Some came close, none yet matched perfectly. Laboratories joined the effort from another angle, probing the properties of exotic particles that could, in theory, produce such early light. Particle accelerators could not recreate the energies of the Big Bang, but they could test the behavior of candidates like axions under extreme conditions. Results from these experiments would feed back into the cosmologists' models, tightening the range of what was physically possible. Even as the work expanded outward to encompass so many tools, the process remained rooted in patience. Every observation required time, coordination, and an unblinking awareness that the first results might be wrong. A single false positive could waste months of telescope time. A single overlooked effect could misdirect the entire campaign. It was science at its most deliberate, a slow tightening of the net, each knot tested before it could hold. And yet, beneath the patience was urgency. Webb's mission lifetime was finite. Chandra, Hubble, ALMA, all were mortal instruments, aging under the wear of time and environment. There was a narrow window in which these tools could work together at their full strength, and the anomaly had appeared at just the right or wrong moment to demand that cooperation. In the private thoughts of those involved, there was another urgency still. The universe had been generous enough to send a message from a time before stars. It might never send such a message again, at least not within reach of our instruments. To let it slip through without understanding would be to miss a once-in-history chance to glimpse a chapter of creation no one had known existed. And so the plans grew bolder. Proposals for deep surveys with Webb that would stare at a single patch of sky for hundreds of hours. Coordinated multi-wavelength campaigns that would layer X-ray, radio, optical, and infrared data over the same coordinates until the sources were revealed in full. Searches for similar signals in existing archives, combing through years of observations from other missions to find a hint of this early light hidden in plain sight. Every plan, every instrument, every simulation was in service to a single idea: that the truth of the anomaly could be found if the universe was asked enough times, in enough ways. Whether that truth would affirm the models or tear them apart was not the point. The point was to ask, to measure, to push the tools of human curiosity as far as they could go before the dark closed over again. In the coming years, as the instruments turned their gaze to the farthest edge of time, the mystery's answer would either take shape or dissolve. But for now, the pursuit itself had become something almost as rare as the light that started it. A moment when the full machinery of science turned, in unison, toward a single, distant, and impossible point in the sky. The light had traveled for more than 13 billion years, yet in the minds of those who studied it, its journey had only just begun. For months, data had been examined, theories proposed, instruments aligned toward the farthest edge of time. The scientific method had been followed with almost ritual precision, each claim tested, each assumption exposed to scrutiny, each possibility placed under the cold lens of measurement. And still, the light remained unexplained. It was not that the tools had failed, but that they had revealed too much, an image of the young cosmos that did not fit the frame we had built for it. For those who had lived their lives under the shelter of the Lambda CDM model, it was a moment of disquiet. Cosmology had been a map that worked. It had guided spacecraft and simulations alike, connecting the first seconds of the Big Bang to the galaxies we see today. It had predicted the shape of the cosmic microwave background, the distribution of dark matter, the rate of expansion. And now, here was something that slipped between its lines, not in defiance, but in indifference, as if the universe itself had quietly carried on without regard for the structures we had drawn. In closed meetings and quiet conversations, the tone began to shift from technical to philosophical. What does it mean to see light from a universe that, by every calculation, should have been dark? If the story of creation is longer, more complex, and more chaotic than we believed, what does that say about our place in it? Some spoke of it in poetic terms, that we had stumbled upon the prologue to the cosmos, a page we did not know existed. Others preferred the language of exploration, that we had found the edge of the known map, and beyond it lay an ocean whose shape we could not yet imagine. For both, there was the same underlying truth, that the universe was not finished with us. It still had secrets to give, if we were willing to listen. In the long hours between data drops, some scientists found themselves returning to older questions, not about the physics of the light, but about the meaning of looking at it. The photons Webb had captured were older than Earth, older than the Sun, older than the elements that made the detectors themselves. They had crossed a universe in which nothing familiar existed. No planets, no life, no constellations. And yet they had endured, carrying their message into an epoch where minds could receive it. In their survival was a kind of defiance against the oblivion that swallows so much of what the universe creates. It was tempting to imagine that the light was a message, but that was only metaphor. Photons are indifferent messengers. They carry only the imprint of their origin and the scars of their journey. The meaning is ours to give, and in giving it, we reveal more about ourselves than about the cosmos. We see in them the persistence we wish for our own species, to survive the turbulence of time, to cross distances we cannot yet measure, to be recognized by another mind far away. There were moments in the quiet after long debates when even the most rigorous scientists would fall silent and let the weight of it press inward. To look at the first light, or something even older, was to be reminded that the universe is not just a place of forces and equations, but a place in which we live. Its history is not separate from ours. It is ours. Every atom in the human body was shaped by events set in motion in those first luminous moments, whether they came from stars or from stranger fires. And so the question of what is it became entangled with the question of what does it mean to see it? We have always looked backward in time to understand who we are, into history, into geology, into the fossil record of the Earth. Now, with Webb's golden mirror, we looked into a history so deep that it included not only the origin of our species or our planet, but of light itself. The scale was overwhelming, but it was also grounding. In that scale, our conflicts and divisions shrank, and our shared origin came into sharper focus. It is possible that the answer will be ordinary, that the anomaly will resolve into a known class of objects, that the early light will be folded neatly into the existing framework of cosmology. If that happens, the work will still have been worth it. To chase a question to its end is to honor the craft of science, and even a negative result leaves the map stronger. But it is also possible that the light is the beginning of a deeper change, that it will force revisions not only in the equations we use, but in the way we think about the universe's earliest acts. In that case, it will not be the first time that a single observation has overturned the order of things. We have been here before, standing at the edge of an unexpected truth, when the Earth was found to circle the Sun, when the Milky Way was revealed as one of countless galaxies, when the expansion of the universe was discovered to be accelerating. Each time, we stepped into a larger, stranger reality. If this light demands that we do so again, then the task will be to meet it with the same mixture of humility and ambition that has carried us this far. Humility, because the universe is older, larger, and stranger than we will ever fully grasp. Ambition, because that truth has never stopped us from trying. In the years ahead, the anomaly will continue to be tested, measured, and modeled. The instruments will turn again and again to the same patches of sky, hunting for new examples, looking for patterns, trying to fit the pieces together. Some of the scientists working on it now will retire before the answer comes. Some will not live to hear it. The work will outlast its first questioners, as such work often does. And perhaps that is the deepest meaning of all, that our place in the cosmos is not defined by the certainty of our answers, but by the persistence of our questions. The light from before the stars reminds us that the universe has been unfolding for billions of years without us, and yet, somehow, we are here to witness it. We cannot change its past, but we can decide how deeply to look into it, how much of its story we dare to uncover. Somewhere, in the darkness beyond Webb's reach, more of that ancient light is still traveling, still untouched by any eye or instrument. One day, if we are careful, if we are patient, if we keep building better mirrors and better minds to guide them, we may catch it. And when we do, we will ask it the same question we ask of this first anomaly. What are you? The answer may come as physics, or as philosophy, or as something we have no name for yet. Until then, the golden mirror will keep its vigil, fixed on the deep past, gathering the faint threads of light that escape the dark. And we will keep ours, fixed on the faint possibility that in them, the universe is telling us not just what it was, but what it is, and what, in its long and patient way, it still might become.